Okay, so welcome back to another video. So this time for this video we're actually going to be calculating a triple integral over the third dimensions of the reals of e to the power negative x transpose multiplied by capital C times x dx. Keep in mind the x values are actually vectors. And so I forgot to write that the following that we're given is that our capital C is actually a matrix, a 3x3 symmetric matrix in particular. So we have our entries -2, -1, 0, -1, 2, 1, and then 0, 1, and 2. And then we have that x is equal to our components of the eigenvector, x1, x2, and then x3. Okay. Now keep in mind that as you can see, C is actually a symmetric matrix because, as you can tell, if you were to take its transpose, you're actually going to get the same entries. So like the whole matrix itself, it's still preserves after performing that transpose itself. So your original row will become the new column for each row and each column, so on, vice versa. But once after doing that transpose, you're going to get that the entries are still the same after performing that method. Okay, so therefore it's a symmetric matrix. So what we'd like to do is let's actually compute our exponential argument, x transpose multiplied by c times x vector. But also keep in mind that because this is actually, we're doing matrix multiplication, so it's not exactly commutative, or yeah, it's not commutative. So be careful with that. Order does matter when you deal with matrix multiplications. So let's see, we have x transpose cx. So simply, if we take its the x transpose, so originally this is given as a column. So this means when we take the transpose, this has become a row vector. So this is x1, x2, x3. Then multiply with our matrix C, -2, -1, 0, -1, 2, 1, 0, 1, and then 2. And then multiply with our x, x1, x2, x3. Okay? So, and this is actually given as the quadratic form of q, x1, x2, x3, given is equal to this formula right here, x transpose C times x. But it's also the same thing as equal to the, yeah, I'll write it here. It's also equal to x and x comma cx, where this is actually defined as the inner product of the two. So when we perform the calculations, so let's just focus on multiplying the matrix between these two here. So we get that, let me just write what we have for original, x2, x3, and then multiply by, so then we would get 2x1 minus x2 for the first entry. Then we get negative x1 plus 2x of 2 plus x of 3, and then we have x of 2 plus x of 3, or 2x of 3. Okay, nice. Now, simplify this, not really simplify it out, we have to perform again another multiplication, matrix multiplication. So we get, so how matrix multiplication works is you take your eigenvector, so your column row, and then the entry is supposed to distribute. So you take, let's say you take the transpose of that, and then you assign it to the following. So the first entry is being multiplied to our x of 1, the second entry is multiplied to our x of 2, and then the third entry is multiplied to our x of 3. So x1, and I also apologize since my knowledge with matrices and linear algebra is a bit rusty, so I'm trying to do the best I can to get the explanation through. x2, and then plus x3. Then you multiply plus x3, then x sub 2 plus 2x. Oops. It's supposed to be 2x3. Okay, cool. Now we can just distribute everything out. So 2x1 square minus x1 x2 minus x1 x2 plus 2x sub 2 square plus x sub 2 x sub 3 plus x sub 2 x sub 3, then plus 2 times x sub 3 square. Okay, and then we can simplify this out again, combine our like terms again. So 2x sub 1 square plus 2x sub 2 square plus 2x sub 3 square, then minus 2x sub 1 multiplied by 2 times x sub 1 x sub 2, then plus 2 x squared, or x sub 2 x sub 3. Okay, so that's what we have so far. So simply we could just substitute this back, and this is a triple integral over the third dimension. So this means all over the reals. So that means all of our bounds are going from infinity or negative infinity to infinity for the three integrals. Infinity of our e to the negative 2x sub 1 square plus 2x sub 2 square plus 2x sub 3 square minus 2x sub 1 x sub 2 plus 2x sub square x3, then being derived dx sub 1, dx sub 2, and then dx sub 3. Okay, obviously you can kind of tell from here that integrating this triple integral is not going to be fun or easy at all in the slightest. So given that we calculated our argument, which was the x transpose cx, so we just put this not easily integrable, if you could call it that. Not easily integrable, okay? But however, there is a theorem that we can use that's going to make our lives easier. So the theorem is defined as the following. And the requirement for this to work is that it has to be an n by n matrix, so it's a 3 by 3, that works, but it also has to be a positive symmetric matrix as well. So now the theorem is defined as the following. So if we have our matrix C, so if C is an n by n matrix, well, positive symmetric matrix specifically, a positive symmetric matrix, then we have the following. So we have the integral of our r sub n dimensions. So n being like, we have like n integrals. So because there's three, so that's defined as 3 dimensions, those are 3 integrals. So we have n is n integrals. So the following is defined as the integral from n dimensions of e to the power negative x transpose c c times x dx. Don't forget these are is a column, it's an eigenvector, so this is actually a matrix slash vector. Simply the following is equal to the square root of pi to the power n, then divided by the determinant of our matrix C. Okay, so that's nice, and we're gonna use this formula, but before we do that, let's actually prove that this theorem holds. So that way we're after proving this, we can actually then apply our theorem to calculate this. Okay, so write our proof over here. So okay, So one thing we can tell, one thing we would like to establish is that symmetric matrices, they can the term used that preferably would like to say is that they can be orthogonally diagonalized. So I'll put, let me see, diagonally, or actually I wrote that backwards, orthogonally diagonalized. It's really hard to mess up. Okay, so what this means is that we can actually diagonalize matrices whose the eigenvalues and eigenvectors, they have some they actually satisfy some interesting properties. So simply, if we were to define our matrix C, then C is defined as follows. C is equal to our matrix B, the inverse matrix of B, multiplied by D, and then multiplied by B again, where where D is our diagonal matrix, and then B is our is a matrix comprised of linearly independent eigenvectors, comprised of linearly independent, just simple independent, and then eigenvectors. All right, cool. So for our orthogonal matrix O, actually let me go back to red. I'll just put a big O. So O is our orthogonal matrix. What this means is that if I do matrix multiplication of one matrix and multiply by its transpose, it's supposed to give the identity matrix where all the diagonals are supposed to equal to 1, while the upper and the lower entries of the triangular entries, they're 0. Now with that, so for orthogonal matrix capital O, one property to establish is that the transpose of the orthogonal matrix is actually equal to the inverse of the inverse of our orthogonal matrix. So therefore, we can actually say that C is equal to the transpose of our orthogonal matrix multiplied by our diagonal matrix, and then multiplied by our orthogonal matrix again. Okay, that's cool. Now, now what we can do is let's actually take the determinant of both sides. So that means determinant of C is equal to the determinant of transpose of our orthogonal multiplied by our determinant of our diagonal multiplied by our determinant of our orthogonal matrix. Okay, so now keep in mind that our matrix D is actually it consists of positive eigenvalues. Let me write it over here. So D, you can see that, right? Yeah. So our matrix D is composed of positive eigenvectors, lambda 1, lambda 2, lambda 3, and then all the way up to lambda n. So therefore, that means, let me actually write it like this. D consists, I'll put a plus for positive eigenvectors, or eigenvalues, my bad. So lambda 1, lambda 2, all the way up to lambda n. So therefore we can say that D is equal to the it's the diagonal of our it's the diagonal of the matrix. So lambda 1, lambda 2, all the way up to lambda n. So, okay, so that's just one thing to establish. And when we take the determinants, they have opposite unit determinant. So you can actually just take the determinant of, so the thing is that the determinant of an orthogonal matrix is that it's always going to equal positive or negative 1. But to put it simply, because we're just dealing with positive values, so we can just say that it's just equal to 1. And so that means these, this is just 1, so really the only thing we have left is that the determinant of C is equal to the determinant of our diagonal matrix. Okay, and then when we take the determinant, and then when we take the determinant of the diagonal matrix, it's just simply just equal to the product of our eigenvalues. So the determinant of C is just equal to lambda 1 multiplied by lambda 2, and then just it's just the product of our eigenvalues. Okay, so now let's actually focus on our exponential argument. So our the e to the negative power of x transpose cx. Okay, so that means by definition we know that x transpose multiplied by cx is equal to the inner product of x and then cx. Okay, so now what we can do next is we can actually do our substitution. So we said that C is equal to the orthogonal transpose multiplied by the diagonal multiplied by the orthogonal. So this is just x and then OT then DOX. Okay, cool. And then now there's a little property we can use. So the inner product of let's say of an orthogonal multiplied by our let's say our vector u, and then orthogonal of vector v is simply just equal to just vector u and then vector v. Okay, so we're just going to use that, but like first what I want to do is let's actually just multiply the our orthogonal matrix. So we get that it's OX, and then it will become DOX, since simply we just use the property for OU and then OV. Okay, yeah. So even though OT and then OU, and then O transpose multiplied by O is that you get the identity value. So it'll just become 1. Okay, so now we have that. So now let's actually use our new substitution. So this means we have, let's see, the integral from r sub n of e to the negative x transpose cx dx is equal to the integral and e to the negative ox dox dx. Okay. Now the next thing we're going to do is we're actually going to use a substitution. So this means let y, let's just say y is being our, define y first as our vector y1, y sub 2, all the way up to y sub n, and then we take that transpose. So if we let y equals ox, where is it, right here? So y is equal to ox. Then therefore, this is basically we're doing a u substitution. So therefore, dy is equal to the absolute value of the determinant of o, then dx, which is simply just dy is equal to dx. Simply because if we're doing u substitution, this is also the same as making a change of variables. So usually when you're doing change of variables over multiple integrals, it's basically you're calculating the Jacobian, and that's what we need. But we know that determinant of O of our orthogonal matrix is just equal to positive or negative 1. But because we have an absolute value in there, it's just thrown in there. So we're just only focused on positive values, so it's just 1. So therefore we have dy is just equal to dx. So we have that. But also, let's also, because we're substituting y for ox, so therefore let's actually do the calculation for capital D multiplied by y. So dy is equal to our diagonal multiplied by our y transpose. So therefore we actually get that it's just lambda 1 y1, lambda 1 y1, lambda 2 y2, and then all the way up to lambda n yn. Okay, nice. Now next I want to do is now let me do the substitution first. Okay, so now let's we calculated our y is equal to x and then our change of variable, so let's actually substitute that back. So we get that r sub n is equal to e to the negative y dy, and then the determinant of O dy, which is just 1. So this is the only thing that cancels is just our determinant, n, and then e to the negative y, and then dy dy. Okay, and now let's actually calculate the inner product. So is there room for here? Yeah. I'm just trying to make sure I have all the space I can. So y dy is just equal to, so calculate the inner product, so it's just like the dot product in the sense, so it's this y multiplied by our dy, so pretty much that would have to mean that it's the sums, but each y sub n is actually going to have a square, so this is lambda 1 square plus lambda 2 y square, then all the way up to lambda n yn square. Okay, so that means over here we're going to get so this is the integral from n dimensions, so this is e to the negative lambda 1 y1 square plus lambda 2 y square, then dy. Okay, and then we can actually separate these this integral out, so we can combine them as a product of integrals using so this means this is lambda, or the integral from the reals of e to the negative y1 squared dy 1 multiplied by the integral from the reals of e to lambda 2 y2 square dy2, and then you get the gist. It just goes all the way up to yn e to the negative yn squared dyn. Okay, nice. And then so that means now here's the thing we want to note is we've seen this many times in my past videos that this is actually the same format as the Gaussian integral. So therefore, Gaussian integral is so this is the reals from e to the negative say lambda y square dy is just equal to the square root of pi divided by lambda. So we're going to use that. So therefore, this means that this is pi over lambda 1 multiplied by square root of pi lambda 2 all the way up to the square root of pi lambda n. And then simply if you summarize this together, we get that it's just pi to the n multiplied by the square of, what is it, lambda 1, lambda 2, lambda n, but that's also equal to the square root of pi to the power n, that's supposed to be an n over here, and then divided by our determinant of C, which is what we said was right over here. Those are supposed to be products, not like separated by commas. So the proof is done. And now all there's left to do is we actually have to calculate our determinant. So let me see, do I have, okay, let me see if I can make this work. So how about I unzoom this out so that I have some room for this tiny little space over here. Okay, should be good from here. So now the last thing we have to do is just calculate our determinant of C. So determinant, our matrix C is just C is equal to, let's see, we take our -2, then multiply with our, so this cross out, so it's 2, 1, 1, 2, minus, multiply by -1, and then the determinant of that is just -1, 0, 1, 2, and then our kth column terms is just 0, but you know, that's just gonna be 0. You do the math and all that, and it comes down that it's actually, the determinant is just equal to 4, and then therefore we can conclude that the determinant, our triple integral, so our triple integral from the third dimension of e to the negative x transpose cx dx is just equal to the square root of equal to pi cube divided by 4. But if you simplify this out, you actually just get pi cube and then divided by 2. Okay, and we are done. So box this in red, and then that's the end of the video. Ooh, that's a big one. That's really interesting dealing with symmetric matrices.